Remember doing this in school? Solar cells have come a little bit further since then. Let's take a look. So globally speaking, solar energy generation went from 100 terawatt hours to 1,000 terawatt hours in just 8 years. So less than a decade made an order of magnitude jump. It's a pretty big deal, right? But then it went from 1,000 terawatt hours to 2,000 terawatt hours in just 3 years, or less than 3 years. So this has been jumping up like crazy. And this is of course driven by the need for cleaner, renewable energies that we're all looking for, but also by a dramatic reduction in cost of the technologies that fuel all this, including these Perovskite cells, or Perovskite. I think I'm saying it wrong. So I looked this up a few times. I said it wrong on the last BIOS video that we did there, but it's the 50-90 rule. If you got a 50% chance of doing something right, it means you have a 90% chance of doing it wrong. Anyone that's tried to plug in the old school USB understands this, of course. But anyway, I'm getting off track. Back in the 1970s, a single watt of solar energy cost around $77 or 80 bucks for a single watt. Today it's like 10 cents. So 10 cents versus 80 bucks for a watt. It's a pretty big deal. Massive reduction in cost, right? And that's driven, like I said, by these technologies. The Perovskite family is anything that has the crystal structure of calcium titanate. So technically Perovskite is a mineral called calcium titanate, but anything that replicates that same structure is considered a Perovskite family. And that's what they use for these types of cells. And whether you're making a solar cell or shoes or a spaceship or whatever, you want to make sure you're making it right. And that's where spectroscopy comes in, because you can instantly, literally at the speed of light, check to make sure that everything is on track. And we've got this NIR set up behind me, and we're going to take a look at some of these cells in reflection mode using both a reflection probe and an integrating sphere. The two main methods of taking a reflection measurement include a reflection probe or an integrating sphere. And each one of these has their own pros and cons. The nice thing about a reflection probe is that it gives you exact control over the specific point of your measurement. So you can find a problem spot, like right there, and take a measurement just on that point and ignore everything else around it. But if you have any changes to the angle of the probe or the distance that then carry over to future measurements, that's going to affect your future measurements. So you want to make sure that everything is very tightly fixtured and repeatable when going from measurement to measurement. And with the integrating sphere, we're getting more of an average measurement over the whole area of this port. So anything that's covering this illuminated port contributes to the reading that we ultimately see up on the screen there. So if I cover it with my finger, we're getting some trends in the NIR that have to do with my finger, skin, and blood and all that there. And we always want to reference with a white standard like this WS1 here. So if I put that over the port, that's going to give us 100% reflection across the whole wavelength range. And that's our reference. And then we can go to one of our Perovskite samples, and you can see that this is semi-transparent. So we're getting some light coming out of there, but we're getting those peaks and valleys on the screen. So these almost look like a sine wave. So if we freeze frame that and then take a look at our other sample, now we're getting a slight offset. See the change in amplitude and the position of those peaks are offset. And these patterns aren't just random, rather they're a fingerprint of how light interacts with the various layers in the Perovskite cell. So by analyzing the position and the offsets of these trends, the manufacturers can fine-tune things like film thickness, look for defects, and optimize the overall performance.